Perfect. Right. So, welcome everyone. This part of the demonstration is going to be about a couple of bathymetry processing tools, which we are developing to ease the incorporation of bathymetric data into different applications. Uh, these are in different stages of development. So, any feedback regarding some functionalities that we can add to what we are already presenting would be great. Uh, some of the tools were developed by Professor Merwade when he was in his PhD, and then a decade later, I started with it 5 years ago, and then recently Chung Yuan joined us last year. So it has been some like amalgam of different techniques and different coding experiences as well. So to start with, I'll start with read scale data. As Dr. Mustay told us in our last presentation, that you have these transects or you have this different kind of data, the zigzag surveys, but then it becomes extremely difficult to be able to convert these into some uniform 3D structure, which can easily be incorporated into different applications, whether that be flood modeling or ecohabitat modeling or other kinds of modeling applications. So what we are trying to do here is to create sort of an automated algorithm that takes into account different kinds of challenges with these survey data and creates a nice uniform 3D mesh that incorporates all this bathymetric information into the 3D mesh. The tool is expected to be capable of taking care of different spatial patterns, such as cross-sectional surveys versus zigzag surveys versus just longitudinal surveys. And it's also expected to take into account like the different point densities, because based on the instrumentation, you can have different densities at different sites, or even within the reach at the same site. The inputs to this tool are just the survey points, the river center line, and the channel boundary, which acts as a mask to determine the processing area. And then the output is simply a 3D mesh at whatever the user-defined resolution is. So it can be fine or coarse based on what the user wants and what application is required from that. So to give you a bit of an idea, what this does is that it looks at the distribution of the points to just create cross sections at optimal locations, and then interpolate between these cross sections to create a 3D mesh. We have developed this in Python. We are still developing the GUI, but it will look something like this, where the user just gives us the inputs, the outputs, and the parameters, and it gives us the mesh. I'll do a short demo of this based on our Python tools. So to start with, this is the survey points that we have. So it doesn't really follow any pattern. And then we have the center line, and we have some channel boundary based on either the DEM or aerial imagery. So then we go and we run the model, and it simply gives us some messages and some intermediate values. But most importantly, what it does is it creates a mesh. And the good thing about this mesh is that because it's created at the spacing that the user wants, it has all the information that was there in the observations all around. Some of those observations were in the cross section, some of them were between the cross sections, and what happens is that you get a nice 3D structure. So coming back to some of the outputs, for example, in this case, you have these cross sections that were created from the center line, and then these look in 3D like this, and then finally you get the mesh. That was what we do with read scale analysis, which is from survey data. Now, the second thing that has become a focus in the last few years is going for larger scale applications, where you're modeling entire watersheds, and therefore you want to generate bathymetry for that entire dendritic network of the river. And this becomes extremely difficult because all the inputs that you need, including the surveys, are usually not available at such large scale. So you either have gaps laterally or longitudinally. And you almost never have data for lower order streams. Additionally, some of the other morphological data sets that are used, such as the center line or the banks, aren't really readily available. We do have some publicly available datasets, but they are updated periodically. So it may or may not correspond to the latest DEM, such as the LiDAR DEM that is available for that region. Also, because it's large scale, it's hard to actually go and check every point and see if everything is working fine or not. There have been other methods such as the D8, the D infinity, but these have generally resulted in center lines which do not properly correspond to the shape of the channel. So what we want to do for the second tool, which is named Spring, which is System for Producing River Network Geometry, is that we want to improve the spatial attributes of the entire river network. Specifically, we want to make sure that the center line corresponds to the DEM. We delineate the channel boundary for processing, and then create some sort of a synthetic bathymetry based on the availability of data and user choices. So more the data available, better the synthetic bathymetry. Less data, more conceptual the bathymetry keeps getting. So corresponding to that, my input will simply be just the center line and the DEM. And of course, there are parameters that the user provides based on their choice. The output will first be the center line and the channel boundary created automatically. And then based on those two, they'll create the synthetic cross section and the 3D mesh, which shows the river geometry across the entire network. So this is basically what happens. Essentially, you shift this center line till it corresponds to the river in the DEM, and then delineate the part that is missing the bathymetry. These two are used as inputs for the second part. And then we go reach by reach to get the channel geometry. This confluence geometry is a little bit of a special case, so that requires a separate algorithm that makes sure that everything is connected properly and that the tributaries are flowing properly into the main river. For this case, we do have a GUI based on ArcMap, and I'm going to try and do a live demonstration of that as well. Right. So this is the case where we have the Wabash River here, the Tippecanoe River here, and there's a creek here. The red line here is my input. Basically, this has been extracted from NHD medium resolution. So you can see that this creek is not exactly accurate as per the DEM. And even in the Wabash and the Tippecanoe River, where you have these different, the lines are within the river, but it's not exactly following the river center line properly. So what we do in this case is we try to correct the entire right. So this is the GUI that we have developed. All you have to do is essentially just tell us what the inputs are, what your parameters are going to be, and then we are going to run it for you. I clicked OK, and I hope everything works fine. It detected two confluence points. It deleted the older outputs, and now we see the input. So let me remove this. So as you can see now, we have a better center line that goes along the river, and even in these cases, it's following the river curvature better. One of the important things here is that if you're not happy with the output, you can simply just use it again as an input to create a newer and more correct output. Also, if you have a DEM from a lower resolution DEM from where you have developed the center line, and now you have a higher resolution DEM, you can use this tool to correct it, because this tool is more focused on getting the center line right, and therefore, in terms of performance, it doesn't slow down much when you go for a high resolution DEM, which is a big strength of this. So once you have the center line, you go for the bathymetry, and I'm going to demonstrate it here. So let's say this is my main river, and this is my tributary, and I want to generate some sort of cross sections and 3D mesh for defining the geometry of this entire place. What we do in that case is we have a tool for creating the cross section. So let's say I click on cross sections. I provide all the inputs that they want, click OK, delete the contents, and create new cross sections. So as you can see, it's relatively fast, I would say. and it creates the cross sections. Click OK. And now what you get if you click on the cross sections is cross sections along the entire network at the spacing that you need. And then after that, if you want, you can create the confluence geometry. And it's the one thing that we have really focused on in this is that you don't really have to do anything apart from just a few clicks, and then you're automatically done. And that's it. So after you're done with this, you run the profile lines and everything, and then what you get is a 3D mesh that covers the entire network. If you keep on repeating this automatically for every tributary and main river pair, you automatically get the entire network. So to show you some sample outputs, for example, here you can see this is the same area. Based on the general local characteristics, you have different types of cross sections. The confluence is corrected properly, and the mesh in 3D looks something like this. And this is for a reach, and this keeps on going for every reach. So to summarize, we are developing a suite of 3 fast and efficient tools, which will help us in quickly and automatedly improve the 3D representation of rivers in D games. We are focused on having minimal user inputs so that everything gets automated and it's good for large scale applications. The first one that we presented was for a reach scale analysis where we could incorporate surveyed points. The second one was more a network scale analysis where we used whatever data we have in that river network to generate bathymetry for the entire river structure. Right now, these are, as we know, in QGIS or ArcMap, but we are developing this to be web-based tools in Rimorphis. So any additional functionalities that you feel would be useful will help us in develop those and integrate this with this framework. Thank you.
Thank you, Sayan.